Every year in the United States, hundreds of thousands of tons of sheet piles are driven into the ground, enough steel to build several aircraft carriers. But unlike the towering ships that dominate the seas, these giants vanish underground, silently holding back water, soil, and even protecting skyscrapers. How does this transformation from scrap to precision steel, with tolerances smaller than a fingernail, actually happen? Stay with me, because the secrets behind this fiery, thunderous process are rarely seen. To grasp the scale, think of this: one aircraft carrier weighs around 100,000 tons. Every year the US produces enough sheet piles to build multiple of these floating cities, but instead of sailing the seas, these tons of steel sink into the earth to keep our modern world from collapsing. It all starts in massive scrapyards, where old ships, bridges, and industrial machines await their second life. Towering cranes with magnets scoop tons of scrap and drop them into ladles headed for furnaces hotter than volcanoes. Inside electric arc furnaces, roaring at nearly 3,000 degrees Fahrenheit, the scrap melts into a molten lake of steel. Alloying elements are carefully added to ensure strength and resistance to decades of moisture and pressure underground. From this fiery cauldron, the steel flows into continuous casting machines, solidifying into glowing red slabs, raw blocks of future strength. These slabs, reheated to around 2,200 degrees Fahrenheit, enter the rolling mill. Here, the real magic begins. The steel isn't just flattened, it's sculpted. Each pass through specialized rolls gradually shapes it into Z-shaped or U-shaped profiles with astonishing precision. The most critical part, the interlocking edges, with tolerances of just hundredths of an inch, these giant steel zippers must connect flawlessly. If they don't, entire walls of sheet piles could fail under pressure. Imagine steel rushing through the mill at the speed of a car while being pressed into shape with atomic-level accuracy. A single 60-foot pile weighs over 3,000 pounds, the weight of a small car condensed into a narrow strip of steel. Yet when connected, hundreds of these piles form underground walls capable of holding back earth and water with the strength of dozens of trucks pressing against them. Precision is everything. One side of the pile forms a groove like interlaced fingers, the other forms a protrusion like a thumb. If the lock is too tight, workers can't assemble the wall; too loose, and water leaks through. The balance is perfection born from fire and force. After rolling, the glowing piles cool slowly, hardening to full strength. Giant saws slice them to length. Inspectors check every lock with gauges, ensuring not a single flaw will compromise performance. Some receive sealants to guarantee waterproofing. Bundled and lifted by cranes, each weighing up to 30 tons, the piles are loaded onto trucks with telescoping trailers or freight trains that resemble steel dinosaurs crossing the country. From there they arrive at ports, dams, and cities, ready for decades of unseen service. Sheet piles guard coastlines, form the skeletons of ports, piers, and breakwaters, and defend cities like New Orleans against floods. They're indispensable for skyscraper foundations, keeping deep excavation pits stable in dense urban centers. They are the silent soldiers of modern civilization, born in fire yet destined for invisibility underground. But steel's story doesn't end with sheet piles. Every year 12 million cars are scrapped worldwide, their steel reborn in similar ways. That rusting old sedan in a backyard, 90% of its material gets recycled. Batteries, tires, catalytic converters containing platinum and palladium all find new purposes. The hulking shells are crushed, shredded, and sorted with magnets and eddy currents, then reborn as construction steel, new car parts, or even furniture. Tires transform into asphalt and playground surfaces, while glass becomes construction material. Almost nothing goes to waste. This wasn't always the case. In the early 1900s, abandoned cars littered fields and rivers. By World War II, they became critical resources, fueling the production of tanks and weapons. By the 1970s, environmental laws made car recycling systematic. Today, up to 90% of a vehicle is recycled, saving enormous amounts of energy compared to producing new steel. The cycle continues at sea. Gigantic ships, once floating cities of luxury, eventually face their final voyage, not to another port, but to dismantling yards. Every single day at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. But how is this steel predator built? I visited the factory to see it all with my own eyes. Get ready because we're about to step into the beating heart of fighter jet manufacturing. Buckle up. The day begins with the roar of machinery. My pulse quickens as I watch workers move with precision and discipline. Here, in the heart of aerospace engineering, one of the most famous fighter jets in the world is brought to life. But building an F-16 starts long before the first rivet is placed. Engineers use advanced 3D modeling software, like CATIA Vive 5 and Siemens NX, to create a digital twin. This allows them to test aerodynamics, simulate material strength, and optimize the placement of every cable and pipeline. Supercomputers run simulations predicting how the F-16 will perform at max speeds, under extreme G-forces, and in hostile temperatures. Before full-scale production, prototypes of key components, the wings, nose section and tail, are pushed to their limits in the lab. They're exposed to violent vibrations, extreme temperatures from -76 degrees Fahrenheit to 302 degrees Fahrenheit, and even impact tests simulating a bird strike at 559 miles per hour. At the same time, test pilots evaluate the cockpit ergonomics, the heads-up display, and the controls. Every detail matters because the pilot's life depends on it. Lockheed Martin secures its materials years in advance. Aluminum and titanium alloys from Alcoa and Tymet form the skeleton of the jet. Composite materials from Toray and Hexcel are used for the wings, radar-absorbing elements, and stealth coatings. Avionics and radar systems come from Northrop Grumman and Raytheon. Supply chain delays, not an option. On the factory floor, the atmosphere is intense yet focused. Each worker knows mistakes are unacceptable. The jet is assembled in modules: cockpit, central fuselage, tail, and wings. In one workshop, the aluminum cockpit frame is complete. Workers in white gloves install avionics, HUD displays, and computer modules. A 12 mm thick bulletproof canopy is fitted, capable of withstanding direct hits. Over 12 miles of wiring connect sensors. Another colossus of modern industry, the press brake. Imagine a machine longer than a double-decker bus, applying millions of pounds of force, bending thick steel as easily as you fold paper. These machines form everything from Tesla car bodies to armored military vehicles. A 10-foot-long steel sheet nearly half an inch thick requires at least 350,000 pounds of force to bend. Modern CNC-controlled press brakes achieve accuracy down to 4/10,000ths of an inch. Their punch descends at 4 inches per second, slowing to fractions for perfect control. Automotive giants, Ford, GM, Tesla, rely on them for frames and panels. In aerospace, tolerances are so extreme that even 2/1000ths of an inch of error could ruin aerodynamics. At Oshkosh Defense, press brakes exert 2 million pounds of force, bending steel over an inch thick into armored plates. Shipbuilding uses presses several stories tall, not just bending but stretching and twisting metal into hulls capable of withstanding storms. Errors here mean disaster at sea. And where there are presses, there are guillotine shears. Once tools of execution in 18th century France, today their industrial descendants cut metal sheets cleanly and silently with surgical precision. CNC controls set length, angle, and speed, while safety systems guard workers. They can slice through steel inches thick, preparing it for further shaping. From air ducts to furniture to refrigerator housings, guillotines and press brakes keep modern life running. The largest hydraulic press in the world, built in the US during the Cold War, still works today, forming massive aircraft parts, nuclear reactor components, and even sections of rockets. And finally, what about the machines we cast aside? Every year, millions of laptops are discarded, yet they are far from worthless. Inside each lies a hidden trove: gold, silver, copper, and dangerous toxins like lead and mercury. Specialized recycling centers handle them with astronaut-like care. Workers wear protective suits to shield from sharp edges, toxic dust, and even the risk of residual electric charge from capacitors. Lithium-ion batteries are removed by hand and stored in sand-filled containers because a single puncture can cause an explosion. Hard drives are pulled out and destroyed, sometimes shredded, sometimes melted, ensuring no sensitive data survives. Before anything else, batteries and hard drives are removed. Why? Because lithium batteries can catch fire, and hard drives may still hold sensitive data. Once those risks are gone, the laptops are ready for dismantling. The first step is brutal but precise. Each laptop rolls onto a conveyor belt where a massive hydraulic press, exerting up to 5 tons of force, slams down. With a sharp crack, the casing splits apart, making internal components accessible, some destined for reuse, others converted into fuel. Metals are separated using magnets and induction detectors. Ferromagnetic materials, like steel, are pulled aside with powerful magnets, while copper and aluminum are sorted electronically. Glass from displays is shredded, purified, and repurposed for new screens or even construction materials. The motherboards and chips go through an even more fascinating journey. Boards are dissolved in chemical baths to extract their rare and precious metals. Even hazardous waste is neutralized under tightly controlled conditions. The process may take hours, days, or even months, but the outcome is extraordinary. A laptop that once powered your work or entertainment is reborn as part of a car engine, a skyscraper frame, a new smartphone, or even another laptop. Nothing truly disappears, it transforms. But while old laptops are broken down, across the world another kind of assembly is taking place. Not destruction, but creation, on a scale almost impossible to comprehend. In Toulouse, France, lies one of the largest aircraft manufacturing plants on Earth, the Airbus facility. Spanning over 11 million square feet, this is where giants of the sky are born. The legendary double-decker A380, the fuel-efficient A350, and other Airbus aircraft all take shape here. Like cranes, each engine must be perfectly aligned, as even the slightest miscalculation could endanger flight safety. After the structure is complete, the aircraft undergoes grueling tests. Brakes, hydraulics, avionics, all are pushed to their limits on vast test grounds, covering 2 million square feet. Finally, the aircraft enters the finishing phase. Before it can wear the colors of an airline, it must be painted, an intricate process that requires up to 3,300 pounds of specialized paint. First, the surface is treated with anti-corrosion coating. Then layer upon layer of polyurethane paint is applied, ensuring durability against UV rays and harsh weather. Logos and liveries are added, sometimes requiring weeks of meticulous work. The cockpit, however, is where the real magic happens. Built separately, it houses up to 5,000 individual components, controls, sensors, displays, and navigation systems. On the other, machines of unimaginable complexity are built. Both processes are driven by the same principle, transformation. Old laptops may turn into the metals used in new aircraft, while those aircraft, decades from now, will themselves be dismantled and recycled into the technology of the future. The cycle never stops. What we throw away today may be reborn as tomorrow's innovation, and what we build today may one day be taken apart, its materials flowing back into the endless loop of creation, destruction, and rebirth.